Hi, welcome to the second video of the third probabilistic programming session. We are looking at a classification problem this time. Specifically, we're looking at a credit assignment problem. Suppose you are a bank and that you have to decide whether you will grant credit, i.e. a mortgage or a small business loan, to one of your customers. So you've hired a bunch of experts, and they look at a particular case, a particular situation, and then decide on whether someone will get credit, and you've asked them to report on what are the aspects of the problem that they use in their decision. You recorded all of those, and you've recorded for a number of customers whether they were successful in their credit application. This is an historic data set, and you want to automate your credit assignment decision process by training a classifier on this historic data set. So let's have a look at the data. This data set actually comes from the UCI machine learning repository, same as the regression section. So it consists of past credit assignments labeled as successful, which is 1, or unsuccessful, which is 0. And that's also what we want to predict. For new customers, are we going to give them credit or not? So many of these features have been anonymized for privacy concerns. So we only have numbers. We don't know anything about the specific customers here. So if we read in the CSV file and then do some necessary pre-processing, such as converting a data frame to an array, then we can make a plot of the data. These are the first two features, feature 1 and feature 2. We actually have 7 features in this case, and so the 8th column are the labels in this situation. And you can already see that this is not a linearly separable problem, at least not in the first 2 features. So this might prove challenging. It might prove challenging to automate this decision process by your experts with a linear classifier. So that brings us to our first try it yourself block. So these are the first 2 features. So you can only visualize this sort of thing in 2D, and we have 7 features, but you can sort of look at many combinations of features. So I want you to have a look at a few combinations, like 3 and 4, 5 and 6. Try to get a feel for what the data is like. Is the problem perhaps easier in some of the other features? Right, so now we are moving to the model specification part. This is actually similar, quite similar as to the regression section. Before we called the input variables x, we called them covariates in the regression nomenclature. Now we're calling them features, and we're calling y we used to call y the responses, now we're calling y the labels. But we still have parameters theta, and same as with regression, we're looking for a posterior distribution of the classification parameters, so that's p of theta given y comma x, and that posterior is proportional to the likelihood of y given x and theta times the prior of p of theta. So this likelihood is different. Before we had a Gaussian with this linear product as its mean function. Now we have something called a logit distribution, or a logit likelihood. A logit is short for a Bernoulli distribution with a sigmoid transfer function contained within it. So what happens is that we still have this linear function of x. So this maps this high dimensional representation of the problem. So x has a number of features. Then we use these classification parameters to map that into a single number. That number is real valued. We then put that number through the sigmoid transfer function, which maps it into the interval between 0 and 1. And then we feed that as a rate parameter to the Bernoulli distribution, which outputs a 0 and 1. So if this sounds confusing, if you're having difficulty grasp this, I suggest you have a look at Bert's lecture on discriminative classification. He goes into this in quite a lot of detail. So this is probabilistic programming, so we're going to look at code and not math. Right, but the sigmoid transfer function, obviously you need some transfer function to map this real valued number into this interval 0, 1 to be used in the Bernoulli distribution. but the sigmoid transfer function, as useful computationally as it does not allow you to integrate over it. What that means is that we cannot compute the posterior exactly. This will happen a lot, and up to now we've mostly looked at situations where you would get an exact posterior distribution, or you compute the posterior distribution exactly. Most often you cannot do that exactly, and you need to perform an approximation. There are a number of approximations to this particular problem, Bayesian realistic regression, and Bert has talked extensively about the Laplace approximation to the posterior in his lecture. That is one of the easiest ones to understand mathematically, and that's also why he talks about that one. It's well described in Bishop as well. Code-wise, so in terms of programming a model, that's actually not the easiest approximation. Rather, this logit likelihood function is a bit easier, but how it works mathematically is a bit different from the Laplace approximation. It's something called the local variational method. It's described in section 10.5 of Bishop, and I encourage you to have a look at that if you're interested. For now, we won't go into the details of this logit distribution or this local variational method. All you need to know is that there's, aside from the classification parameter theta, there is also a local variational parameter which we call chi here. There is one chi for each likelihood function. So if we have a data set of n samples, then we have n local variational parameters. So all you need to know for now is that in this description of Bayesian realistic regression, mathematically we're still doing the same thing. We still have a prior on p of theta, and then we have a likelihood where we take a linear function of classification parameters theta and covariance x, map that into a into a sigmoid transfer function, and then feed that into a Bernoulli distribution. But specifically how we're going to approximate the posterior, that involves this local variational method. Right, so we still have this, in terms of the prior, we still have this Gaussian prior on the classification parameters, and that's the same as with regression. And note that this local variational method will also produce a an approximation with the Gaussian distribution for the posterior. So the syntax in this model is quite similar to the syntax for the non-recursive estimator in the regression section. So we have again clamped parameters and a prior that we defined as theta with a Gaussian mean variance. We now have three vector structures of variables, each of them containing n samples. And so we iterate over those n samples, and we define for the ith entry of this vector x it to be a standard random variable. Here we've defined this linear function f of theta separately, so there's dot theta times x of I. That's not strictly necessary, you can plug that in here, but because the logit is already sort of the combination of a sigmoid transfer function of Bernoulli, I'm avoiding making it also the combination of this linear function in there. So we have this local variational parameter chi I here, and then we have the logit node with f of theta, this linear function, as its first argument, and then this local variational parameter as its second argument. And we are, similarly as before, we are indicating that xi and yi are observed, and that x has the number of features as 7 plus 1 for an intercept parameter. So it's very similar to before, but the main difference now is that instead of one unknown variable, we now have two unknown variables, theta and chi. Theta, that's one set for the entire data set, and then chi is one parameter for each data point. But since we now, so chi is in fact actually multiple unknown variables, but so is theta, and so we use theta to indicate theta 1 up until theta 8, and then chi for chi 1 up until chi n. But so we're going to treat these two as unknowns, theta and chi. We now need something called a posterior factorization. That's a function that you see here, where we're going to tell Formulab that it needs to generate two different step functions, a step of theta and a step of chi. And then if you execute step of theta, then you're updating the parameters for theta, and if you execute step of chi, then you're updating the parameters chi. We don't have to re-specify these parameters to the message passing algorithm. It is the message passing algorithm always takes the currently defined posterior factorization as input argument. Outside of that, it's still the same, this syntax. Now we come to the part where we execute the algorithm. Again, we are initializing a data structure to house the posteriors. You'll see here that I'm initializing the posteriors for the local variational parameters chi I. You don't have to memorize this. This is just necessary for this particular local variational method. We are currently looking at all of the data at once, so we're doing the same thing as we did before. We are performing a list comprehension for the features, so that we can index into this particular entry in the dictionary. So the ith component of data x is a column vector with all of the features augmented with a 1. The labels are still univariate, so we don't need to do that. Now comes the biggest change with Bayesian linear regression, namely that considering that we now have two unknown variables, we've split our unknown variables in two, namely step of theta and step of chi. These depend on each other. So the parameter estimate for theta uses the current parameter estimate for chi, and the current parameter estimate for chi uses the next parameter estimate for chi uses the current parameter estimate for theta. So what they do is you're sort of bootstrapping. You're pulling this one up, and then you're pulling this one up by that one, and then you're pulling that one up. And then, so in short, you need to iterate over these updates a couple of times. So Bert has a lecture on variational Bayes and why you need to iterate this. It's a bit later on. We're doing this a bit early here for the computation of this Bayesian logistic regression model. Generally speaking, you don't need a lot of iterations for this to converge. Right, so this will generate two posterior distributions for theta and for chi. Chi we're not really interested in, theta we are interested in. I would love to visualize this, but this is a 8-dimensional distribution, so it's hard to express that in 2 dimensions. Yeah, we can only draw contour plots of 2 of those components. And even if we did plot a contour plot for the theta 1 and theta 2, or theta 3 and theta 4, for instance, that might misguide our intuition on these parameters. So to get an idea of how well these parameter estimates are, so what we can do with these, how well we fit our model, we're just going to make some predictions on test data. So we have a test data set as well, courtesy of the bank. Again, we're pre-processing that into arrays. And then currently we are, for the moment, we are looking at the map estimate for the classification parameters. So we have a posterior for theta, then we take the mode for that posterior distribution, a point estimate. We use that to compute this linear function f of theta. Then we plug that linear function into a sigmoid transfer, and then we round the result to obtain the most probable label. So that's what we see here. So ignore the fact that there's an unsafe mode. We're just extracting the mode from this posterior. Then we're computing the dot product between the features augmented with 1s, and then theta map, the point estimate. Then we are pushing the result of this dot product through the sigmoid transfer function, and then we're rounding each entry to produce a set of predicted labels. Then we can compute the classification accuracy on this test data set by just checking how often our predictions match our test labels. Printing that shows it's on the order of 63%, which is quite low, and if you were a bank, you might at this point decide that you don't want to automate all of your experts because your model can't reliably predict or can't predict with high accuracy whether future customers should get credit or not. Alright, that's the end of the third probabilistic programming session, and I'll see you next time where we treat latent variable models and dynamic models.